Right. College Algebra, Chapter 2, Section 5, Symmetry. We already talked about symmetry when we talked about parabolas. We have an axis of symmetry, that vertical line, where we have exactly the same image on both sides. Symmetry. Well, line symmetry can occur in all sorts of different directions. Here's line symmetry. This kind of looks like a stingray. I don't know what that one is right there, but there's line symmetry. Line symmetry, again, is if I have one point on a graph, I can find another point on a graph so that these are perpendicular bisectors. That line of symmetry is always a perpendicular bisector of it. So we can have, we're going to study two types of symmetry, y-axis symmetry and x-axis symmetry. So here's this cool kind of W, and that's an equation. That's not too hard of an equation to make, in fact, to make that W shape. And this one, what's this one on the right? What shape is that? That's a parabola. That's just a right sideways facing parabola. So this first one has y-axis symmetry and the second one has x-axis symmetry. How can we tell when we have symmetry? Well, here are the tests. When I have equations, we're going to look at some equations down here. How can I test to see this equation? I'm not looking at the graph, because if I look at the graph, oh, it's easy. Oh yeah, it's y-axis symmetry. If I'm just looking at the equation, how can I tell? Well, here's how we tell. I'm glad you asked. The y-axis is going to be symmetrical with the y-axis if I can replace the x with a negative x, and when I simplify it, the equation remains the same. It simplifies back to the original. Now let me show you why an x and negative x is the same thing. Let's go over x and up y. If I go back x, I get the same answer. An x and a negative x give me the same answer. That's what happens on y-axis symmetry, always. If I go to the right, there's the value. Go to the left the same distance, there's the same value. So that's the deal that's happening on this first one. And then it works backwards if I want to know x-axis symmetry. Replace the y with a negative y, and if I simplify it and it's unaltered, then I have x-axis symmetry. So let's take this one. If I replace the y with a negative y and the x's are the same, it's x-axis symmetry. Let's try that. Determine whether the graph of the given equation has symmetry with the x-axis or with the y-axis, or maybe it's neither one. So let's start here with x-axis symmetry first. If I'm going to test x-axis symmetry, I'm going to replace the y with a negative y. And I am going to simplify it so it looks like y equals, and see if I have left it unaltered. I'd have to multiply everything by a negative. Y equals negative x squared minus 2. Is this the same as the original? No, it does not have x-axis symmetry. If I want to check, does it have y-axis symmetry? I am going to replace the x with a what? Negative x. I'm going to stick a negative x right there. I'm going to, whoops, plus 2. I'm going to square a negative x. What do I get when I square a negative x? A positive x squared. Does this look like the original? Yes, this one has y-axis symmetry. Same idea right over here. If I'm going to test for x-axis symmetry, I'm going to replace the y with a negative y. Absolute negative y minus 2. I'm going to simplify. What's the absolute of a negative y? So when I do that, oh, absolute negative y, I should ask, is that the same thing as absolute of y? Yes, it is. Is it the same? Yeah. This has x-axis symmetry. Is it possible, do you think, to have both x and y-axis symmetry? Yes, it is. A circle has x and y-axis symmetry. There's one example. So let's try my y-axis and see. Remember, I placed the x with a negative x. So let's come up here. Negative x equals absolute y minus 2. I want it to look like the other, so I'm going to multiply it by a negative to change that to an x instead of a negative x, so I get x equals negative absolute y plus 2. Is that the same as the original? No, this one is not. It's only x-axis symmetry. This one was y-axis symmetry. This section will involve several rules that you'll need to memorize and keep straight. It's not hard to do. You'll just need to remember how do I test for x and y-axis symmetry? Let's go to the next thing. Definition of symmetry with respect to a point. I can be symmetrical with a point. Instead of just having a line where the two sides are mirror images of each other, if I have a point symmetry, the definition is here. Notice this point. If you can find a point and a matching point, so that when I draw the line, every one of these goes through the same location. It is point symmetry. I want you to think, when you're visualizing, rotate 180 degrees. How far have I gone when I've rotated 180 degrees?
Backwards.
Okay. If I'm facing one way, 180, I've completely turned around. I've gone halfway around a circle. I've rotated halfway around a circle. So if you think of, let me just draw a line right here. If I take this curve, and I rotate them halfway around, they look exactly like each other again. It's the same graph. It looks exactly the same. This has point symmetry with the origin. In your mind, can you rotate it 180 degrees? That would come down here. Hey, that curve just becomes this curve. And if I rotated this curve up to the top, it just becomes this top curve.
So that's x and y.
This is point symmetry. It's not x-axis symmetry. X-axis symmetry, I'd have a top and a bottom.
But
I don't.
X and y.
Well, it's not x and y symmetry. It's point symmetry. Now, we'll deal something with the x and y's.
But wouldn't it be the same? Because it's taking...
No, if you talk about x symmetry, it means I'm symmetrical with the x-axis. It means I can flip it over the x-axis and it looks the same.
But
I can't do that.
The y too.
Oh, I see what you're saying. You're saying you're flip it over the x and flip it over the y. You're correct. In fact, that is where it comes from. Look down here. Daniel is just a mathematical genius. I'm going to flip the x and I'm going to flip the y, both of them. And if it leaves my equation unaltered, it means I am symmetrical with the origin. That's the only point we are going to do for point symmetry. You can have other points we're symmetrical with, but we're just going to study symmetrical with the origin. So, if I take this and change it to a negative x, and that y to a negative y, and simplify it, well, a negative times a negative is a positive xy. It's the same thing, right? A is symmetrical with the origin. If I take the second one, make that a negative y, make this a negative x, and simplify. Now I'm going to say negative y equals negative x cubed, because if I cube a negative, I get a negative answer. I am going to change my signs. I want to have a positive y, because this one was a positive y. So I'm going to multiply it by a negative. Y equals positive x cubed. Hey, so far so good. And there's the problem, -1. So this one is no. This one is not symmetrical with the origin, because that ended up different. The others ended up the same. So there's our second test.
No.
Odd and even functions. If you have an even function, when you replace the x with a negative x, you get the same answer. Which symmetry did we do that on? I replaced the x with a negative x and it looked the same. Do you remember which axis symmetry that was? Y-axis symmetry. Even functions, this is true, they are symmetrical with the y-axis. They are called even functions. If, and this is different, we haven't seen this, if I replace the x with the negative x, and it ends up negative of the original equation. In other words, if my original equation was 2x minus 4, and then I end up with the negative of the original, negative 2x plus 4. In other words, it's negative, opposite of everything that I had. That is called an odd function. Odd functions are symmetrical with the origin. Odd functions have origin symmetry. Looking here, this is the graph of an even function. y-axis symmetry. It's a mirror image across the y-axis. This is an example of an odd function. It's an odd function. It's symmetrical with the origin if I rotate it 180 degrees. This one is a pretty picture. It's not even, neither even nor odd. There you go. It's a nice graph, but it doesn't have symmetry with the y-axis or the origin. So it's not an even function, it's not an odd function. It has symmetry right there. There's an axis of symmetry, but it's not an even or odd function. Okay? Identify even or odd functions. Let's try this test up here so you can see how we do that test. All I need to do is substitute negative x. So negative x is being cubed. And then I'm going to simplify it. That would simplify to negative x cubed. And you have two questions to ask. Did I end up the same? If I end up the same, it's an even function. Or did I end up negative of the original? It's an odd function if that happened. This is an odd function. This is just negative of the original function. It's an odd function. Now it's possible for neither of those to happen, and then we say neither. Let's try this one. I'm going to substitute a negative x. I'm going to take f of negative x. Absolute value of a negative x. That's the same thing as the absolute value of x, right? Same thing. I can get the same thing. It's an even function. It's symmetrical with the what? Y-axis. This is symmetrical with what? The origin. A little quiz along the way. Let's try this one. H of negative x means I take a negative x, raise it to the fourth, plus 2 times a negative x. Raise this to the fourth. That's the same thing as x to the fourth. This one here becomes negative 2x. Oh, it's not the same, and it's not the opposite. It's neither. It's a nice graph, but it's not symmetrical with what we were talking about. Translating. You learned this in Algebra 2, so if you're going to remember, this is not going to be hard. If I have a function and I add a number or I subtract a number onto the end of the function, I move it up that far or down that far. Some of you walked in here and I was playing around with something that we had done in pre-calculus. Well, I've got one for you guys. This number on the end is the number that will move it up or move it down. This happens to be the absolute function, that nice v right over here. So k is the value on the equation. So if I come down to k and I move it up, I'm just making that k positive. Or I move it down. And the fun thing to do, see, is you can watch it, there we go, watch it move up and down. So that number on the end is going to move it up, or it's going to move it down. We'll put it back at 0. There's where we start.
K is the y.
The k is the number on the end. It's c in this one. Just the number on the end. So let's try that out down here. Oh, we're not ready to try it out. Horizontal translation. If I add or subtract a number onto the x. Notice it's inside that function, not off at the end. If I add, I move it which direction?
Left or right?
Which direction? Left.
Yeah.
If I subtract, I move it right. So back to our pretty graph over here. Where'd it go? Back over here. Tell me which letter in this moves it left and right. H moves it left and right. So if I go to positives, what will happen?
Go right.
You go left.
I'll go left. If I go it goes left. If I go negative, it goes right. It is opposite. The y is because your x arrives at the same y value earlier. If we did a whole bunch of points and took some time, if you want to, I'll do that with you, but it's generally more confusing than remember the direction it moves.
Just remember that.
Remember the direction it moves. There is a y. It's because When I have a plus x, I have added a value to what I'm putting in, and so I get to my y direction sooner. So if I get to my y direction sooner, then I have moved it left.
All right, I'll remember it.
Yeah, I mean, that's why it's happening,
Moves
but
left
it doesn't necessarily clarify it.
Moves left and don't push.
Back over here. So let's put these two things together, and let's see if we can sketch.
Left, left, and right, right. Why is it right, left, and left?
Use the graph of f. Here's the graph of f. This function right here, y equals f of f. F of x. It's the graph of f. To sketch a graph of each function, f of x plus 3, how has it changed?
Moves up 3.
It has moved it up 3. 1, 2, 3. This would be where this used to be, and so just try to make a new one. Some of you are better artists than I am. Looks like that. Just moved up 3. What's happened here?
Down 2.
Down 2. So I'm going to take that point, and I'm going to go down 2. It has now become here, and there you go. There's new one. Just moved down 2. Right down here, we're doing the same thing. How do I need to sketch my new graph?
Moves right 2.
Right 2.
You got it right.
I'm going to take that, and I'm going to move it right 2. I'm going to take that, and I'm going to move it right 2. That is going to move right 2. Oh, my.
It is.
Something like that. Everything is slid to the right 2. Hey, that was pretty good for me, huh? What's happened here?
Left 1.
Left 1. Everything has just moved left 1.
I don't even say right.
Going to look something like that. Everything is slid left 1. So let's do some other things. Given the graph of this function, sketch this graph. What has this done?
A left 1. Down
Left
3.
1 and down 3. So if this was the original, I need to go left 1, down 3, there's my new one. Every point has moved left 1, down 3. Left 1, down 3. Every point has just moved left 1 and down 3. Tell me what type of symmetry you see right here.
X-axis.
X-axis symmetry. Now what we are doing here is actually taking the original graph
Reflect.
and reflecting it across the x-axis. Look at how we do that. You've learned this before. We put a negative in front of the equation. It reflects it across the x-axis. Now this one is new. This is a reflection across the y-axis. Here's the original. I flipped it across the y-axis. Can you spot where is that negative?
From in front of the F.
In front of the x. Inside that function, in front of the x. So depending on where the negative is, when the negative is in front, it reflects it in the vertical direction across the x-axis. In the vertical direction, across the x-axis. When the negative is inside, it reflects it horizontally across the y-axis.
Why?
That's what they say down here. Save that y to work time. Come up. Right here. This is a reflection across the x-axis because of where the negative is. Where this negative is, it's a reflection across the y-axis.
I'll not question you anymore.
So, oh certainly, you can question me, but I'm not going to do it right now. But come up later, I'll be happy to go through. So what type of reflection? Here's the original. They want us to graph the new one. What do I need to do? What reflection has happened?
It's gonna go reflection down.
X-axis.
It's going to go
Claire, I didn't hear that.
reflection
What type of
down.
reflection? Oh, good morning. Anybody? Anybody? I'm not sure I heard it. X-axis. This is a reflection across the x-axis. So this point looks like it's 1, 1. It needs to be right down here. Let me change colors. And there you go. That's going to be my new one. This one, what type of reflection?
Across the y-axis.
Across the y-axis. So I need to take this point, and I'm going to move it right over here. There's my reflection across the y-axis. So now we have all these individual things that we have done.
And there's more.
There's more individual things, sorry.
Yes.
Okay? If I multiply, and you learned this in Algebra 2. If I multiply a number by a function, If that number is bigger than 1, it has stretched vertically. It's gotten taller. If that value is between 0 and 1, it has been compressed, or we said shrunk vertically, compressed or shrunk vertically by that value. So let's look at this example where they have 2 times the absolute value of x. Here is the original, 2 times the absolute value of x. Well, at any point, I'm going to take this point right here. The original one was too tall. Now my new one is 4 tall, twice as tall, stretched vertically by a factor of 2. This one, it's a little blurry. You see that 1/2 right there? 1/2. It's going to be half as tall at any location. It is only half as tall as the original one. It was compressed. I need to come back to my picture. Let's do some quizzing. If I make this A, so here's my A. If I make this A a number bigger than 1, what is it going to do to my graph? It's going to stretch it vertically, which has the effect of making it narrower. So if I take that A and I move it, there it goes. Now if I take that A and move it between 0 and 1, let's see if I can move it between 0 and 1. There we go, 0.9, 0.7, 0.6. Notice what it has done? Original is that orange dashed one. It's been shrunk vertically. Now what happens if I go negative with this A? What happens if I go negative right there? It's going to be reflected across the x-axis. It will up and down. It's been reflected across the x-axis. There it is, when it goes negative. Now what I need to do is put a new letter right there, don't I? A, H, K, let's call it B. And let's turn that B, let's turn that B, where did my mouse go? Into a slider. So here's my B, and I'm going to have that B is 1. Let me take all these back to the original zeros. There we go. Whoops, sorry. My original 1. There we go. That's the original graph. Now if I take that B and make it negative, what will that do? Reflect it across the y. Remember, if I've multiplied my x by a negative, it's going to reflect it across the y. Now I want you to look at that graph. If I reflect it across the y, how will it look?
Same thing.
It will look exactly the same. So right now my b is 1. Now I'm going to get it to a negative 1. Now it's going to change something when I get there because I'm manipulating it. But when I get to negative 1, it's exactly the same thing, isn't it? Now we need to know what happens when I multiply numbers here. When I multiply numbers here, we went vertically, stretch and compress. I want somebody to guess. When I multiply numbers here, we've only been working in 2 directions, right, Aaron? Because that's what James is telling me.
Would it move
Man,
forward?
I'm going to have to wake you people up.
Would it move forward and backward?
I believe we are working in directions.
What has the H done? Can you answer that for me?
Moved it left and right.
It's moved it left and right. Anything I do on the X is a horizontal change. When I put a negative here, I flip it horizontally across the y-axis. When I put a number here, it's going to stretch and compress it horizontally, just like I stretched and compressed vertically. And it's going to be backwards. Remember, if I add an H, it means I'm going left. Or if I subtract an H, it means I'm going right. Well, guess what? If I get a number bigger than 2, bigger than 1, we normally think, oh, that must make it bigger. It is opposite. It's going to make it smaller. If I multiply by 2, it actually makes it 1/2 as wide. So let's take this one to a positive 2. I am 1/2 as wide. Now you may say, hey, that's stretched vertically. Well, it looks the same, but that's not what I did. I compressed it horizontally to make it look like that this time. And if I multiply by a number between 0 and 1, Between 0 and 1, like 1/3. In the vertical direction, if I multiply by 1/3, it's 1/3 as tall. But in the horizontal direction, if I multiply by 1/3, it's 3 times as wide. It's opposite. So let's go to this 1/3 on this thing, which would be 0.33. Oh, I can't go to 0.33. 3 times as wide. We widened it out. Isn't this fun? Let's come back here. And we just talked about vertically doing it when I put the number in front. Oh, let me talk about the horizontal, then I'll come back and do this one. Here it is. There's the horizontal. That's what I just illustrated to you. If it's bigger than 1, it's compressed horizontally. And if it's between 0 and 1, it is stretched horizontally. It's opposite. Remember, the stuff done on the x is the opposite of what happens when we do it on the y.
So what if you compressed it horizontally and stretched it vertically?
So if I compressed it horizontally, which would... Whoops, sorry. You said compressed it horizontally? Yeah. If I compressed it horizontally, it would make it narrower. And then what did you want to do?
Stretch vertically.
And stretch it vertically.
You'll just make it a lot
I can
bigger.
really do it. That's exactly right. If I take it and we are going to compress it horizontally, which means my b needs to be bigger. So there you go. I got my b 2.8. And then I'm going to stretch it vertically. So my a needs to be bigger. So let's move my a bigger. There you go. It just continues to narrow it down like that. And this is what's fun to do.
Oh my.
See? We can just make them all go at once. Man, it is a party.
Right. Throw another one off the
All right. Let me stop all these things.
Yeah.
Ooh, there it ended up way down there. But anyway. All right. Let's play with it now. Let's see if we can make this stuff work. Tell me what I've done to that original function.
There's so many things to do.
You brought it up.
Look where the 2 is. I've multiplied 2 times the function. Stretch vertically. I have stretched it vertically. Twice as tall. So if I am going to have to sketch this new graph, it needs to be twice as tall. Now this point is 0. What's twice as tall as 0?
0.
0. This point is at 2. What's twice as tall as 2?
4.
4. This point is at 0. It's gone nowhere. This point is at -2. What's twice as tall?
-4.
-4. Back to 0. Back. All right, so here we go. I am twice as tall, both in the positive and the negative direction. Woo, that makes you go crazy. Yeah, you get the idea. You're going to have beautiful pictures. All right, it's twice as tall. This thing should be exactly 4 and -4. So much for my picture. There you go. That's what I should have done. Use my smartboard to cheat. 1/2. 1/2. What do I do with where that is done? Compressed vertically. I need to know which direction. Compressed vertically, because I can compress them horizontally too. That means it's half as tall. Half as tall. Hey, I'm doing better on this one. Half as tall.
I wonder why.
I can't believe this. That's awful. That is awful.
He's got to redeem himself.
I do. That was terrible, terrible,
Thank
terrible.
you very much. Back.
Yeah.
No, this makes sense.
Moving on.
There you go.
All right. Tell me what happens. Look at where that 2 is.
It is compressed.
Oh, quit cheating by looking in the book.
No, I'm just thinking. I'm not cheating.
It is
It's horizontally.
horizontally compressed. It's going to be half as wide. So if I am half as wide, I'm going to say, well, that's a width of 2. That means I need to complete the same thing half as wide.
This page is actually covered in my book.
And this one is going to be half as wide. And that one is half as wide. It's looking like this. I am half as wide. Everything has been compressed like on a spring. Ooh, what a beautiful picture. You notice how well I drew this one?
Like
It is half as wide. And what has happened on this? Notice the 1/3.
Stretch.
Stretch horizontal.
Horizontally.
Horizontally stretched 3 times. It's going to be 3 times as wide. So when, and I'll get your question, when you go to draw this, you've got to pick a point. Where can I tell how wide it is? I use that. It was 2 right there. So this is going to be 6. One of these is going to be way out to there. And it's still going to have the same height.
Wait, are we doing it on the graph that is covered?
It's going to be way out to there. We're doing it on the same graph that they have shown.
6. You drew it to 7.
Did I draw it to 7? I did go to 7. And see, that's going to bother me. 6.
There we go.
See, connect the dots. Here's 6. Now notice, look right here. From the middle, I have 1 up peak and 1 down peak.
Whoa.
That whole span, that's all I see. They kept on going. But there you go. I got that one.
Oh my God.
Use the graph. All right.
It is stretched for horizontally.
It's compressed by it's compressed.
Compressed horizontally.
Oh,
It's
okay.
1/2 as wide. 1/2 as wide. So there it is. A little 1/2 as wide. And 1/2 as wide. And then you need to try to keep doing these things.
But we have rulers.
Yes, use a ruler. I've got a whole bunch of rulers sitting at the top of that desk drawer right over there.
The OAA official rulers.
Stretched horizontal.
Stretched horizontally, 3 times as wide. This is actually exactly the same thing we just
Those are the
did.
same
It
graph.
was 2, it was 6. It's exactly the same thing. All right.
Why didn't you just say like horizontally as it says it in the directions?
Am I done? I'm done.
Whoa.
Oh, I
You get to do it now.
You get to do it. You get to do it.